So it is my pleasure to introduce Gary Mitchum this morning. He is professor at University of South Florida.
Thank you, Emily. Good morning, everyone. A little bit of background on this title. Ben invited me originally. We were talking about the sunny day or high tide flooding sort of things. I've been working on it in the Tampa Bay area with the city of St. Petersburg. Ben has been working down here. And after looking at the agenda, I called Ben and I decided, it's going to be kind of grim for the audience to hear the same talk, basically, back to back. We do kind of the related, very closely related things. And so we talked about it for a while, and I decided I would kind of step back a little bit and talk about more the background of the problem, what goes into making predictions for these high tide flooding events. And so there's some caveats here is, first of all, I haven't given this talk before. I've been kind of thinking my way through it and preparing for this. And so I have really no clue about how it's going to go over. And and Ben Kurtman on the bottom. So get logged into Slido. If it goes well, then you can ask me questions. If it goes badly, then you go, what the heck, Ben? So it's Ben's fault if it's bad, you know the joke. So what we're going to talk about then is I made up this title, and the key point here is, we kind of know what we need to know for the flooding events and how to predict them. But what I'm going to argue to you here is that the challenge that we face is that everything that goes into this, most everything that goes into this is evolving quickly. And it's dealing with that evolution. And you heard a lot of this yesterday. We had a lot of really good talks about, the evolving climate state. And so I'm going to touch on a lot of those things today, but not in a great deal of depth. So talking to Ben, we wanted to aim this at very much of a general audience. So there you go. Okay, so this thing here is a forecast. It's by my former grad student, who's now at the University of Hawaii, Phil Thompson. And Phil's done a great job. I use this a lot now in talking to people and our elected officials in particular, primarily because it is backed by a very good paper in JGR. So, it has been vetted in that sense. And so what he's done here is that for the three lines that you see are based on the NOAA intermediate low, intermediate, and intermediate high curves for the sea level rise projections. So the general increase that you see is due to sea level rise. Okay, so this is the number of events you expect per year that exceeds some sort of threshold. I've chosen a fairly small threshold here, and the reason is just simply it's easier to see what I'm trying to show you. There's no particular reason for choosing that threshold otherwise. You can choose whatever threshold you like, and this is for St. Petersburg. You can do this for any tide gauge in the US. So he's made a very nice tool, and it's as part of the NASA Sea Level Change team. So it's available. Well, it's not available quite yet. It's kind of beta testing, but since I was his advisor, I get first dibs. So that's one of the privileges. So the general increase is, of course, due to sea level rise, and I'm going to talk about that first. The other thing is, you see these changes, the undulations. The effect of the tidal modulations were actually much larger than I ever expected. So I'm going to talk about that a little bit too. So the background sea level change, how high is the high tide, and then the bar that you see around it is essentially the ocean atmosphere physics. Okay, so the variability that you see, so we have 2 flooding seasons each year, just due to the tides, when the tide extremes happen. And during what I'm calling a flooding season, it kind of depends on what is the background sea level. Okay, so if it's several inches higher than usual, then you're going to exceed the threshold more often, and vice versa if it's lower than usual. And the interesting thing about that, what I'm going to emphasize to you at the end of the talk, is that bar is based on past statistics. Okay, so it's a statistical model of the, quote, weather, sort of thing. And so I'm going to talk about that towards the end, the ocean atmosphere part. Now, so the take-homes, conclusions first. If you all understand all of these, I can just sit down. So sea level rise, this projection, and we've been avoiding, not so much here in South Florida, but in where I live in Tampa Bay, and also in Tallahassee, and probably over a lot of the, in Washington too, we've been kind of tiptoeing around the idea of mitigation and emissions, changing emissions. I think it's time, and I've changed my mind on that. That's all we really need to be talking about now. Because honestly, when we decide how fast that curve is going to go, even for the extremes, not for the sea level rise inundation, but even for the extremes, what determines how many events we're going to get in the coming decades is primarily the sea level rise portion. And choosing how high that curve is pretty much now entirely dependent on the emission scenario. So I'm going to talk about that first. The tidal signals, it's kind of interesting. I have another student and I who have been trying to reproduce Phil's curve just as a baseline. We're creating our own version. And getting the tide analysis right is actually much more difficult than I expected. I've been doing tide analyses for 30-some years now, and it's taken us several weeks to figure this out, because we're usually doing tide analysis for a year's worth of data in order to project a year's worth of data, tide predictions for a year. When you start trying to project the tides for decades, it's a much more persnickety problem. And I'm not going to say a lot about that, because the tides is the part that is fairly easy, so to speak. And the ocean atmosphere variability, as you heard from several people yesterday, this is a much harder problem, and I'm going to try to just give you my spin on it towards the end of the talk. It's a much harder problem. There's a lot of research to be done on that last part, the ocean atmosphere dynamics. Okay, the first point is there anybody here who doesn't believe that the sea level, you shouldn't say believe in science, accept that the sea level rise rate is accelerating? Okay, I actually search out for audiences now that do not accept that. I mean, those are the, we don't need to be talking to you all, honestly. So I actually look for these audiences, and there are quite a few. And so one of the things, the so-called the North Carolina curve, where the rate has to be linear and computed from the past data. This was passed in legislation, okay, and it was, of course, related to development. Okay? So the so-called North Carolina curve, and this one is kind of interesting, is that from a scientific point of view, it's a very cleverly done strategy, because in science, the data is sacred. And the models, sorry, Ben, but models are models, okay? And even the scientists will not trust the models as much as they would trust the data analysis. And so for them to tie it to the data and say, I don't care what the models say, until I can see it in the data, we're not going to use it for planning purposes. Okay, and so that was actually, it's more difficult to refute than it sounds like. It's easy to make fun of. Remember the headlines? Stephen Colbert, I think, had one of the best ones, is that North Carolina has passed a law outlawing climate change, something along those lines. So it's easy, but in truth, it's hard to refute that. So I'm going to show you two things. One is about a year ago. There you go. You don't need to worry about the precise curve here, the details here, but Steve Niram and I and a few other people did an analysis of the satellite altimetry record. And the key thing is that you can see the black line there. It has an acceleration. There's an upward trend. And the more important thing is that you can't see on this figure is that we did a very careful analysis of the error. and showed that we could reject the null hypothesis that the sea level rise is not accelerating at greater than 95% confidence. So the idea, the North Carolina curve now, is essentially no longer scientifically defensible. Okay, that's the main conclusion, and I've said that a number of times now. Not here, other places. And the second part that I'm going to talk to you really quickly about is the figures that back this up. There's a dozen of them, and it was just way too much. Don't worry about the equations. I'll explain to you what they are. Is that was from the satellite altimetry. How about the longer record from the tide gauges? So we look at the tide gauge reconstructions, what we call reconstructions, where you try to put together a tide gauge record of global mean sea level over the past century, roughly. Then are we seeing the acceleration we expect there? Oh, by the way, the Niramitol curve, the acceleration we got, is consistent with large error bar, relatively large error bar, is consistent with the middle point of the IPCC projections for our CP 8.5. So it's not only different from zero, it confirms the rate that the models are predicting. Okay, so a very important point there. From the long tide gauge record, we did something a little bit different. Here, the errors are larger. So determining that the acceleration is different from zero is a little bit problematic. We did something a little bit different here. I've worked with a number of students over the past 5 years or more to develop a method for taking a single time series, do whatever treatment you want to it. You can smooth it, you can remove a seasonal cycle, you can fit models to it, and then using the residual from that to make I came up with a novel way to make a noise model out of that, which I think is superior to anything else that we have available. It took a long time to do it. And based on that, we asked the question of, these different models here are all models that have been suggested for sea level rise. Okay, the first one is just a linear, the North Carolina curve. Second one is a simple quadratic. Then we have the model 3 is from a paper Don Chambers and colleagues wrote, where we have a linear rate of rise, no acceleration, but a 60-year harmonic in it, very low frequency variability. Then we have two kind of step functions. If you look at the long sea level curve, the impression you get, the eyeball fit that you're not supposed to do, but we all do it anyway, is that what we seem to see is a relatively constant rate of rise and then a set of step functions. Constant rate of rise, then it jumps up. Constant rate of rise, then it jumps. It's almost like different volume reservoirs are coming into play. So there are two kind of step function models. And then the third one we threw in was a model which is actually accelerating much faster than the quadratic, which is an exponential model. And then we asked the question of not which is the best fit, but given the noise in the data, can we distinguish between these fits? So in other words, you have a linear, these 6 different models. If you can't tell the difference, it doesn't matter how well they fit, if you cannot distinguish between them. So we did these calculations. It's a Monte Carlo simulation based on the noise model that I just mentioned. And when we do this, we get an interesting result. And this paper is going to be submitted in the next few weeks. And what we find is that you can distinguish, you can tell the difference between non-accelerating and accelerating models. Okay, so you can tell the difference between them. And since the accelerating models fit better to the data, we again conclude that acceleration is important. Also interestingly though, between the different acceleration models, we cannot distinguish between them. So the only conclusion we can really make, but important for today, is that it is accelerating. So the sea level rise curve, sea level rise is accelerating. And here, this is the curves that we chose in the Tampa Bay area for guidance for local government offices and elected officials. And the X that I made on the bottom, that's the North Carolina curve, essentially, the NOAA low curve, as they call it. It's essentially a non-accelerating curve. And this is from the assessment we made 4 or 5 years ago. The updated one, that curve is no longer on there. And the Miami update that we had that Obi worked on, that I was on his group as well, we've removed it from there as well. Okay, so we're no longer accepting non-accelerating models. All of the guidance is accelerating. There's something else here too. This is something I've been trying to figure out for a number of years now, is that when you're talking to the public and also to a lot of elected officials, is that there's a disconnect that happens. When you look this is from the IPCC, we have different emission scenarios on the left-hand side, okay? And then we have the temperature change, could be sea level rise just as easily. But what happens is we always show people the one on the right side. We show them this curve on the right, and what happens, what I've just learned by just talking to people, is that they look at that and they think all of those curves are scientifically equal. And they can say, well, I like the low one. And when I say, well, no, the one on the top is the path we're on, and they say, oh, well, why are you always just talking about the high end? Okay, not the most probable, but the high end versus the low end. I accept the low end, but they accept that without realizing that that means you're committed to that lowest curve on emissions, meaning by now we've turned the corner and we're going to be to negative emissions in a couple of decades. Okay? That disconnect is something that we are not doing a good job at communicating. And I'm starting to get to the point where you cannot show the curves on the right without showing the curves on the left. They have to be coupled somehow. Okay? So at any rate, that's just my own experience from talking to a lot of public and electeds. Okay? So I don't really quite know. I've been trying to work on that problem for a long time, but whatever. So given an emission scenario then, what I'm going to say to you as well is that the physics is reliable. We have a model spread. But what distinguishes one curve from the other in terms of temperature or sea level change is the emission scenario, not the spread in the models. Okay? There's an interesting paper that came out in GRL last month, I believe. It's very new. But they went back looking at different models for sea level change going back 5 decades, back to the 70s. And then they recreated these models and ran them through up to 2017, which is the data they had at the time, and checked how well are they doing. And in particular, they did the one of the temperature change per unit of emissions, what we used to call the climate sensitivity. Okay, so the climate sensitivity was a parameter that you would set, how much am I going to get? Now it's an emergent property of the models. And in fact, what they found out is when you recreated these models, ran them through, that they all did a very good job. Again, the ocean atmosphere physics is not the issue. We're doing a good job with that. So again, the future emissions is the real story. Okay? So what's the effect of the tidal and ocean atmosphere corrections? So that was the story about the sea level rise. Now the ocean atmosphere and the tides are, like I said, here. This is the part when Phil first showed me this. We have here, look here, from 2020 where we're at, we've been in a relatively flat area, up to about 50 events per year. Over the next 5 years, this is for St. Petersburg now. Every location is going to be different, so you have to run your own tide gauge through here. Okay? So everyone is different, but from 2020 to 2025, the number of events has tripled. And this is purely due to the nodal modulations in the tide. Sorry, the nodal changes in the tide. This is a tide effect, but it's tripling the number of events. I showed this to the Director of Public Works in St. Petersburg, and he almost fainted. Because we're already having, our problems aren't as bad as you're seeing here in Miami, but we're already having problems in St. Pete. When I told him those number of high tide flooding events is going to triple in the next 5 years, this was not what he wanted to hear. But at any rate, we can do that. We can do the tides. As I said, it's It's not quite as easy as you think. So I wish he was here. If you need to do these long-term tide projections, call Richard Ray at NASA Goddard. Okay? Richard is a tide expert. He's also grumpy. I wish he was here, but anyway, find a good tide expert, because it's not as simple as just pulling it out. The NOAA projections for the sunny day flooding that Billy Sweet does do not take these into account yet. I talked to Billy about it, and we looked at Phil's stuff, and he's going to, but they do not yet. Okay, so it's not as simple as you think, but it is doable. Okay, the final thing I'm going to talk about today is the ocean atmosphere portion. And here, this is not exhaustive. This is just an example here. And when we try to do this, there's different ways of approaching this. You can take a statistical or empirical sort of thing. And we heard talks yesterday, doing some very nice things. Libby, who I haven't met, gave a very nice talk about this yesterday. And then so that's kind of more the sort of thing that I would do. And it's the superior way, as opposed to what Ben would do, for example, which is to use the models and projecting those. We're friends, come on. So, we used to be. All right. So, but using a statistical sort of thing, you have to do this. You essentially have to assume that there's some persistence. The statistical analysis you did on the past data, you can trust for some time into the future. Fortunately, the project that I have in St. Petersburg, we're only trying to forecast a few months in advance what the next flooding season is going to be like. So in this case, I do use a statistical approach and rely on persistence. Okay? With the modeling approach, you're relying on the physics. And unfortunately, I think there are problems with both approaches. I saw a talk at a WCRP meeting I was at recently, and Jonathan Gregory from the UK is doing some analysis of the CMIP-5 versus CMIP-6. And one of the conclusions, I didn't include a figure because he shared it with me, but it's still in press. It's in review. But the conclusion that he reached is there hasn't been much change in the skill for the ocean atmosphere portion of the signal between that generation change in the models. So we still have a lot of ways to go, and we heard a number of people yesterday talking about where's the jet stream, is there an Arctic oscillation, et cetera. So still a research problem. So, and part of the reason why this was in my head when I called Ben and talked to him on the phone is we're seeing papers coming out now. These papers are both, by the way, from very good friends of mine, so perfect. Very good friends of mine. Steve Niram and I have been working together on the altimeter record for 25 years now, since the beginning of the record, essentially. And Mike Mann, I've known forever. They both put out papers that have me scratching my head. And so the Niram and John Fasulo, they do an analysis of the models, and they make the claim that the El Nino signal is basically greenhouse forced, or the greenhouse forcing signal looks like El Nino. Okay, so, okay, like I said, Ben and I are talking on the phone, has me scratching my head. The mannitol paper bothers me even more. I'll talk about the El Nino thing now, but it's a statistical analysis based on a roughly 80, 100-year-long record, and conclude that the long period variability in the ocean atmosphere, the PDO and the AMO, are not statistically reliable and are noise, that they don't exist, in essence. There are a number of statistical arguments I have with that, but we're starting to see this thing that people not wanting to accept the climate change sort of issue say there's a lot of variability, so therefore there's no forcing, which is logically not correct. Okay, but that is the argument that you hear oftentimes. We're now starting to hear from the other side is that it's all forcing. There's no variability. And in fact, I'm going to finish up then with another thing here, is that let's think about the El Nino part. And this is not El Nino. Mark Kane was here yesterday. Is he here? Thank goodness. Me talking about El Nino in front of Mark Kane is just dumb. Okay? But at any rate, let's think about the El Nino thing for a moment. If you have greenhouse forcing, okay? If you have greenhouse forcing, if you think about it, just the simplest sort of thinking, this is hypothetical. If you reduce the equator to pole temperature difference, then you expect that you're going to reduce the energy in the mean circulation. Okay? A lot of what the mean circulation is driven by is that pole equator temperature gradient. So if you reduce that gradient, we'll reduce the energy of the mean circulation. El Nino is a reduction in the mean circulation. It's a low energy state. A lot of people think El Nino is this big, horrible monster beast, but in fact, it's a relaxation of the system. It's a low energy state. So the forcing that you expect would, in some case, you can make an argument that it might look like El Nino. It's a lower energy state. But also, if you have a mean state, then what's the variability? Well, we're all taught in grad school that most of the variability, the easiest way to think about it is the instabilities on the mean flow. So if you change the mean flow, you expect to change the variability. But we keep thinking about it as El Nino is getting stronger. We heard that a couple of times yesterday, and we hear a lot. Is El Nino getting stronger, or is the mean state getting weaker? Okay? Because we always look at the mean state as if it's not changing, and then we have variability around it. In fact, they're both changing, and they're interacting. So that's why I said this is really still, this area, I think, we're just getting started on in terms of the ocean atmosphere physics. And I'm going to just bring up my take-homes that I told you and leave it at that. Thank you.
All right, thank you. That was fascinating. All right, we have time for a couple of questions. We don't have a discussion session until the very end of the day, so if you have questions for people this morning, we can.
Gary, how do you convince people that it's accelerating? The acceleration of sea level rise, locally, I think it's easier. You know, you can, you know, and Brian may talk about that later today. That you can see those step functions in the trends, in the global time series, and you showed the picture. When you eyeball that picture, you know, the person in the back of the room can easily say, it still looks like a straight line to me.
Right.
So how do we communicate that, well, let me put it this way. I don't think that picture, I mean, I've read the work, so it's convincing that that there is acceleration, but I don't think that picture is making the case. How do we make the case?
Yeah, it's a good question. Well, one of the first things I tell them actually is I'm very careful about showing them a local situation, because you can go to a different location and find the opposite result. You know, the local problem, or the regional problem even, is much, much harder. So the first thing I try to explain to them is that this altimetry, we see a fairly subtle curvature, but in fact, we have a very high confidence in the numbers that go into it. So, and that's because at the global scale, the global problem is actually much easier, because there's only two ways to change it. Okay, you can warm or cool the ocean, or you can add or subtract mass. Okay, so, and then the reason why what I harp on is the quality of the altimeter record. And compared to the tide gauges, we have on a 10-day basis, a 10-day average of global mean sea level from the tide gauges has an uncertainty based on the tide gauges of 5 millimeters. Okay, so we can talk about that. We can also talk about its extremely robust result, because I can take the temperature measurements from Argo and the mass measurements from Grace and add up the components and get the same answer again. So what I really harp away on is the confidence we have in these observations. So. Yes?
So on the theme of variability being hard to predict, I'm guessing it'll come up across presentations today, but I'd be interested to hear your take on the reasons for the exceptionally high tides this year that were greater than initially forecast, kind of linked to 2 and 3 there on your slide.
The exceptionally high tides, is this in at particular where?
Here.
Here, okay.
Very
See,
high.
I live in St. Petersburg, so, and actually ours were not so bad this year. So I think that, I think it goes back to what Nick Shea was showing yesterday, is that there is another signal, which is ocean atmosphere, which you have, the sea level rise rate over the past decade or two has been 3 times the global rate, almost a centimeter per year. So there is a substantial change due to not just the tides, but the background. And it's not sea level rise. I thought that was a little confusing. Sea level rise, we try to differentiate between sea level volume change of the ocean versus a redistribution. And with the Gulf Stream flowing by, you don't need to change the Gulf Stream much to change the tilt and get substantial redistribution terms. I think that's probably here because we're not seeing it so bad in St. Pete. So the tide portions will be different as well. But you could do the, shortly, when Phil releases this, and it'll be on the NASA Sea Level Change Team site. When Phil releases this, you can type in your tide gauge, and you can look at the components that he's attributing there. And it's possible this very rapid increase here, it actually is, we're already in it. So it is changing fairly quickly. Another thing that Phil, I'm sorry, this got me off on a sidetrack. Something else that Phil did was that you kind of wonder about, why, if you add 3 or 4 inches, why do we get this huge ramp up of the number of flooding events? And it's basically that if you look at digital elevation maps, it's like, you have a wall and then a lot of very flat land behind it. And that's just because human beings do what they do. When they build something, they build it as high as it has to be and no higher. And then everything behind that. So once it crests that wall, even by a few inches, it spreads a long ways. And we saw that for the DEMs for a lot of different places. It's kind of an interesting, I guess it's a geology problem. So geology, but the topography of the land matters a lot too. So it doesn't take much to get that flooding once you crest that berm.
Thank you very much.